Hey everybody, Dr. A here, and in this video we're going to be providing some quick background information on other cross-section properties that are relevant to us in both our studies of statics and mechanics of materials. So one of those cross-section properties that we encounter in addition to centroid and moment of inertia is what we call section modulus. Now this is typically computed about a specific axis, usually one of the centroidal axes. So we can derive these formulas, but I'm just going to present them to you here for your reference. So we can have section modulus about the centroidal x-axis is defined as the moment of inertia about that centroidal x-axis divided by y bar, okay? So basically all it is we call it S sub x. It's equal to your moment of inertia about the centroidal x-axis divided by specifically y bar. Now similarly, we can also have, so I'll put an and symbol, we can have S sub y equal to I sub y divided by, what do you think? You guessed it, x bar, okay? So these are what we call our section modulus values. And again, they are cross-section properties. Now, what units do you think section modulus will have? Well, if you look at moment of inertia, it has units of length to the fourth power. And then centroidal coordinates have units of length. So if you have length to the fourth power divided by a length, you can determine that section modulus has units of length cubed, okay? So we're going to say S has units of length to the third power. Now, this is not a volume. This is not a volume. This is a type of area moment. So it's ultimately derived by taking an area and rotating it about an axis. So when you take an area and you multiply it by perpendicular distance, you'll have area times perpendicular distance, which will give you a length to the third power. So it's not a volume, but it has units of length cubed. But it does not physically mean volume, okay? So that's section modulus. The next one we're going to briefly talk about is radius of gyration. This is also computed about one of the centroidal axes. And our governing formulas for radius of gyration are the following. We have r sub x equals the square root of I sub x over area A. And r sub y is equal to the square root of I sub y over area A. So the way we calculate radius of gyration about a particular centroidal axis is we take the square root of the moment of inertia about that same centroidal axis divided by the total cross-section area of the shape. And all of that is underneath this radical sign, okay? And then similarly, we have ry computed as the square root of iy over a, okay? So that is radius of gyration, and radius of gyration has units of length, which makes sense, right? If you have moment of inertia, which has units of length to the fourth, and you divide it by length squared, you get length squared, but then you take the square root of that and you're left with just length. So that's how you can always go back to your unit management and make sure that your units are making sense as you're going through that process. So that concludes this overview of these other important cross-section properties that we're going to encounter in statics and mech of materials and some other design classes later on. Thanks for watching. Please hit like and subscribe.